Hello everyone, this is the second part of Favorskii rearrangement where I will focus on stereospecificity, Quasi Favorskii and Homo Favorskii. Now I will suggest you watch the previous video where you will get the introductory idea of this rearrangement and also lots of examples. The link for that video is right now appearing on the screen, top right corner, and you can also get it in the description box. So here we will see examples of stereospecificity. Now what it means by stereospecificity? It is a property of a reaction mechanism where when there will be a pair of stereoisomer, from one particular stereoisomer you will get a type of product, and from the second type you will get another product. Or sometimes it may be that the mechanism is operating only on one stereoisomer, not on the other. So these are the stereospecificity. Okay. So here we have two isomer, right? Both are cyclohexanone derivative, and this chlorine and this tertiary butyl group, suppose I am numbering it as 1 and 3 position. So in the first case these two are cis, in the second case these two are trans. Now if you convert it to chair form, what happens? 1 3 cis, it will be either axial or it will be equatorial. But when it is trans 1 3 position, it will be axial and another group will be equatorial. So here we have seen how the first stereoisomer we can draw like this. So this is position 3 and this is position 1. So at 1 3 position both are here equatorial because that is a stable position, right? Now when we will start this rearrangement, in presence of this base, there will be negative charge generation at this position. Now this negative charge, it will attack this carbon which is already bearing this leaving group, and we will get cyclopropanone. That is 3-member ring formation is there. Now the next step is here OAT group that will be attacking at this position, and there will be negative charge over this oxygen. Now once this negative charge it is coming back, so it will be something like this. So once it will be coming back, there will be negative charge, that is carbanion generation. Now both side it is equivalent, so any of this side negative charge can be generated. So once the negative charge is generated, it will take proton from the medium, and ultimately we will get a 5-member ring like this, as you can see. So this product we are getting from this blue stereoisomer, which is highlighted with blue color, right? Now what will happen in the second case? In the second case we can expect same type of mechanism, but first of all we have to understand that this chlorine and tertiary butyl group, this is position 3, this is position 1. So chlorine is equatorial axial, and tertiary butyl group you have to keep it equatorial, okay, because it is large group. Now again negative charge generation will be there. So this will be the position where negative charge will be generated. Now see, further mechanism is not possible. So what is happening here? This CC bond and this CC bond, they are not anti-periplanar. But if you look at the previous mechanism, here this CC bond and carbon chlorine bond, see, this is anti-periplanar. This Z type of shape, that is anti-periplanar. So this type of position, it is the requirement if we want to get the further mechanism. So this negative charge it is attacking and this chlorine is removed. This type of mechanism is only possible if these two bonds, their positions are like this, anti-periplanar. So as it is not possible in the second stereoisomer, so further reaction not possible. So only the first isomer is giving us some product, which is this 5-member ring. This is ester basically. One more example we will see. Here we have again stereoisomer. Suppose this is position 1, this is position 2. So here methyl group and chlorine, they are trans to each other. So when it is at 1 2 position, you are converting it to chair form. It will be either EE, equatorial or axial. And in the second case, this methyl group and chlorine at 1 position and 2 position, they are cis. Now when they are cis, you have to make one group equatorial, another group axial. Now we will see how they look when they are in chair form. So methyl group and chlorine, as you can see, both are here equatorial, right? But in the second case, this is equatorial and this is axial. Now it has to be, because this COCH group, that part you have to keep in equatorial because this is a very large group. Now in presence of base, what is happening? In presence of base, there will be negative charge generation at this carbon. So one of the hydrogen will be removed, negative charge will be there, and chlorine will be removed. So minus Cl, we are getting 3-member ring. Now this OAT will attack and negative charge over oxygen further it will come back, C double bond O will be formed. Finally, negative charge will be at this position. That is, this CC bond will be broken because negative charge here is stable, not the other position. Here if you generate it, it is not stable. This is a stable carbonyl. So that is why ultimately negative charge will be here, and we will get, so from this part, that is OET is attacking here. So you will get COOET, and which ultimately will be in this equatorial position, and methyl group at axial. So these two groups, now they are equatorial and axial. Now what is happening from the other stereoisomer? Negative charge you have to generate here because one of the hydrogen will be removed. This negative charge it will attack and Cl will be removed. So Cl minus, you are getting 3-member ring. Now OAT will attack and negative charge, further C double bond O, and negative charge will be finally here because the other position negative charge is not stable. Now look at this, when negative charge will be generated here, this will be your final methyl group, right? So in this case, now methyl group, these two methyl group both are equatorial. So in the previous case, equatorial axial, that means these two group will be cis finally in the product, and in this case these two group will be trans. This is cis, this is trans. Okay, so see how stereospecificity we are getting. From the blue starting material you are getting this blue product, and the pink one is generated this pink. So it is not possible that suppose I am numbering it as 1, 2, this is A, B. So you will get A from 1 and B from 2, not the other possibility. Okay, so that is why it is stereo-specific reaction. Next we will see Quasi-Favorskii. Now Quasi-Favorskii, how it is different from normal Favorskii. Here we will see some different type of mechanism, and when it will be occurring, when there is no alpha hydrogen. That means the ketone is non-enolizable. You cannot make enol because alpha hydrogen is not present. So that is why non-enolizable ketones. And here semi-benzylic type of rearrangement we will see. So negative, here we are treating this molecule with HO minus, right? You can also use OET minus. So HO minus, what it will do, as there is no alpha hydrogen, so negative charge generation is not possible. HO minus will directly attack here, and negative charge will be over oxygen. Now this negative charge, when further making C double bond O, so this pH group it will be migrated here, and chlorine will be removed. So once chlorine is removed, minus Cl minus. So from this side we are getting CO2H group and pH. But remember, as it is a basic medium, you are treating this molecule with hydroxide and basic medium. So obviously this OH minus, it will not remain in OH form, it will be in carboxylate form. And further during workup or if you provide proton source, it will be convert CO2H. So final product is acid, whether it is carboxylate or whatever, that is a CO2H form. But after all you are getting acid because we have treated it with HO minus. So non-enolizable ketone also we can get Quasi-Favorskii. So even if you are not, that is the classical mechanism, even if you are not finding, suppose if you are getting this type of molecule in the question, don't think that Favorskii is not possible, because maybe something like Favorskii is possible. Okay, so we just have to check what the other possibilities for mechanism. So this is semi-benzylic Favorskii rearrangement or Quasi-Favorskii. One more example, see, in this molecule also alpha position no hydrogen. Also in the previous case this is alpha position, this is alpha position, and both position no hydrogen. Now for the second molecule, this is your alpha position, this is another alpha position. In both cases there is no alpha hydrogen, right? So OET, it has to attack on this C double bond O and negative charge over oxygen. Now this negative charge will come back, C double bond O, and this CMe3 group, now this group will migrate so that Cl is removed. So final molecule will be something like this, because suppose if it is number 1 carbon, this is number 2 carbon. Okay, so number 2 carbon is basically this containing C double bond O, and this is now our 1 carbon. Okay, so finally we are getting A star because we have used here ETO minus, ethoxide. Homo Favorskii. Homo Favorskii, that how it is different, because in this case we have beta halo compound, unlike the classical Favorskii where we have alpha halo mostly, right? So this beta halo, what will happen now, in presence of OET minus, obviously carbanion generation will be there. So negative charge will be generated by removal of this hydrogen. So this negative charge once it is generated here, it can attack here. And see, as it is 1, 2, 3, 4, it is attacking at the 4 position. So that is why you will get 4-membered ring, unlike a classical mechanism where we get 3-membered ring, because in that case chlorine is at alpha position, but now it is at beta position. So this is alpha, this is beta, beta position, chlorine we have. Finally, OET, rest of the mechanism there is no such difference. So O negative, when it will come back, so either one side, either of this one side, there will be negative charge. So negative charge, the preferred position is this carbon, not the other carbon, not this one, because here negative charge is not stable because of 2-methyl group. So if negative charge is generated here, the final molecule will be this one. Okay, so see here, this CC bond is broken and you are getting, this is the methyl group position. Okay, so you can also rearrange, that is draw it in a different way so that it looks better. So final molecule is this one. One more example. So with respect to carbonyl group, this is alpha position, this is beta position. So at beta position you have 2 bromine, but it is not alpha, that is the normal Favorskii that we see. Now this hydroxide ion, it will attack here. Okay, sorry, I'm just thinking about the other previous quasi. No, that is not the case, because here we have alpha hydrogen, right? So this alpha hydrogen, it can be captured by this HO minus. So negative charge will be generated here, and this negative charge, it can attack one of the bromine will be removed. Now when one of the bromine is removed, what you will get? You will get a new CC bond. So suppose I am numbering it 1, 2, 1, 2, 3, 4. So now it is 1, 2, 3 and 4. Now next mechanism is HO minus. Now it will attack at this carbonyl carbon and you will get negative charge over oxygen. So let me do the numbering again. This is 1, 2, 3 and 4. Now when this negative charge will come back here, C double bond O is formed. This is symmetric molecule. So either you do it with 2-1 bond or 2-3 bond, doesn't matter. So 2-1 bond, suppose I am breaking, and if it is coming at this position, that means 1,4 position, a CC double bond is there. And why it is, it can take place? Because Br is a living group that is present. So if 1,2 bond is broken and 1,4 position, there will be a new CC bond. But ring size is not reduced, it is still 6. So from this part, so that is, let me do the numbering again. So this is 1 position, this is 4 position, right? This is 3 position, and this is the position of, that is the carbonyl carbon. So in this way we will get the final molecule. This is the second example of Homo Favorskii. So that's all for this video. Thank you for your precious time.